Hello and welcome back to the course on statistics. Today we're continuing our journey into the world of hypothesis testing. And we're adding on a new version of hypothesis testing, proportion testing. So let's have a look. A new business challenge again. According to a 2016 survey, a staggering 58% of American households have tablets. Your manager has asked you to test the hypothesis with a 97% significance level that only 58% of American homes have tablet devices. You surveyed 100 random households and found that 73 of them had tablets. So, what have we got going on here? Well, the first thing is, of course, the challenge. This is a real statistic. So, it's about 58%. If you look at different sources, it's around there. I did add, though, the staggering part of American households because it just makes it sound really cool that back in 2016 people thought that that was a lot. Probably it's more by now, especially by the time you're watching these tutorials if it's further down the track. And your manager has already had a feel for that. He already kind of had a feeling that it's probably greater than that. And so he asked you to go out and test this hypothesis. And the whole concept here is pretty cool in itself, that even without having to report to a manager or working for a business, you can just take any statistic on the internet that you're interested in, and you can check if it's changed. All you have to do, as you'll see from further down, you just have to survey like 100 random samples or maybe less, depending on how you construct your test. And based on what we're going to discuss, you're going to know better how to construct these tests. And you can check without having to wait for another year before new results are released and so on. You can check if it's true or not. So you might be interested in a different statistic. You can approach it with the same methodology and then just for yourself, with your small random sample of 100 people or households or whatever it is, find out what the real situation in the world is, if it's increasing or decreasing and things like that. All right, so let's get started on the hypothesis. We have to state our null hypothesis first. So null hypothesis is that 58% or fewer households have tablets. So P is less than 58%. And P is the new thing that we're working with. P is the proportion. So as you can see here, previously we worked with means, so many hours or so many dollars and so on. But here it's actually a proportion. So what proportion of your population says does something or doesn't do something. In this case, what proportion of your population has tablets, what proportion of the households have tablets. And tablets, by tablets we mean like tablet devices such as iPads and so on. And yeah, so but other than that, it's going to be very similar. The only thing is just keep in mind that now we're going to have two letter P's, a letter P for the proportion and a P for the P value, and they're two separate P's. And your alternative hypothesis is that more than 58% of households have tablets. And you can tell that we want to look at more is because it says only 58%. So meaning that anything to the left is kind of like expected. You already have prior knowledge that number of tablets is probably only going to grow. And therefore you just want to check if it has grown or not. And so as usual, we're just going to draw our distribution over here. Some new things are going to happen, or we have to take into account some new things for a proportion test as opposed to just a standard hypothesis test with means. So here what we're going to have is, first of all, we need to do two checks. Very important. We need to check that n times p hat is greater than 10. And by the way, p hat, so p is your population parameter for the proportion. So what's the real situation in your population? P hat is what you measured. In our case, p hat is 73 divided by 100, so that's 73%. And what this is saying is that 73% times the number of people in your population should be greater than 10. So 73% times 100 is 73, should be greater than 10. That is correct. So basically, it means that let's just draw the next one. It'll make sense. So here we're saying Q is 1 minus P, so the percentage of people that don't have tablets in their homes. And that should also be greater than 10. And so 1 minus P is 0.27. 27 times 100. 0.27 times 100 is 27. So this is also correct. And so both of these are saying just that in your sample, the number of observations that said yes and the number of observations that said no, they both have to be greater than 10. So in this case, it has to be more than 10 households which do have tablets and more than 10 households which don't have tablets. So that's an important condition that you always have to check before doing a proportion test. If it's not met, that just means you need to increase your sample size until that is met. Very straightforward. And we have some new formulas which we're going to need to take into account. So the mean of the population is actually equal to p, and the standard deviation of the population is equal to square root of pq. Now, we're not going to derive these formulas here. I might include a tutorial in the course later on to derive these formulas, but I don't really think it's necessary as long as we know that these formulas are like that this is what we need to use, and we then can apply them in practice. But other than that, maybe we'll talk about them sometime in the future. For now, let's just go ahead and apply these formulas. All right, so that's going to be our mean. It just equals to p. That's how proportion testing works, and standard deviation is equal to square root of pq. Here you can see the sampling distribution, so that's why you see the mean of p hat and the standard deviation of p hat. And just as we did with the sampling distribution of means, this is a sampling distribution of proportions. So basically, we're taking lots and lots of samples from our population, and in each of those samples, instead of calculating the mean, we're now calculating the proportion. And the central limit theorem tells us that this is how the proportions will be distributed. They'll be distributed normally around this mean p hat. So this is a distribution remember how we had x bars inside this distribution? This is a distribution of p bars. So all of the possible samples of size 100 that you could possibly take from your population, and then look at those proportions in those samples, this is how they will be distributed. And now let's proceed to our calculation. So I just left only the necessary things at the top to make some space. And our calculations are very, very similar to what we had previously inside the hypothesis testing for means. So mu p hat, this mu, is equal to mu of the population and is equal to p based on our new formula, and is equal to 0.58. That's the same thing, that's from the central limit theorem. Then sigma, or standard deviation, is equal to square root of pq, so let's calculate that. And remember, here we need to take the population parameters, so 58% that we are assuming is correct. So we're living in this universe, we think that this is correct, so we can take 58% times 1 minus 58% is 42, gives us a square root, gives us 0.49. Then we take the standard deviation of the sampling distribution, and according to the central limit theorem, same thing as before, sigma divided by square root of n, 0.49 divided by square root of 100, which is 10, and so it's 0.049. And then we've got p hat, which is 0.73. We calculated that, 73 divided by 100. So just based on this, I'm just curious. Remember we talked about developing a gut feel for statistical significance? And so before we start proceeding with the next steps from here, what do you feel like? Do you feel that this hypothesis is true, or do you feel that it's not true? So let's just go through this. We know that previously it was 58% of people who have tablets in their homes. You found that 73% out of 100, 73 people out of 100, 73 households out of 100 have tablets, not mobile phones, tablets. So what does it feel like? Does it feel like too much, or does it feel like you could have randomly sampled 100 households, and it's fair that with quite a high likelihood you could have gotten 73%, 73 households that do have mobile tablets? So what does it feel like? Does it feel okay, or does it feel a bit suspicious? If you couldn't tell right away, like after we've done these calculations, what does it feel like now? You already know that, now you know a bit more from these calculations. You know that, okay, so thinking of this distribution, the sampling distribution, you have 58% here in the middle, and your p, or your standard deviation, is 0.049, so it's quite narrow, so it's like that. And the p you picked, the p hat, is 0.73, so it's somewhere here. So let's just draw it. What impression does that give you now? Does it feel like too much, or okay, still okay? Well, now we can, even if without yet calculating the z-score, we can estimate where this p will be. We know that the standard deviation is about 0.049, so it's less than 0.05. And the question is, how many jumps will it take from here to here in 0.05 terms, right? So from here, one 0.05 jump will take us to 6.0 to about 62, or 0. Let's say 62 in percentage terms. Is 63%. Another jump, so another standard deviation will take us to 68%, and another jump will only take us to 73%. So this is sitting at around 3 standard deviations away, 1, 2, 3. And as we already know, 95.4% of our observations fall into 2 standard deviations, and into 3 standard deviations, we have to have 99.7 observations of these p hats fall into 99.7. So basically, even without doing the z-score calculation, we've already found out, well, we kind of did it in our mind here, but this is saying is that 99.7% of the time you'd run this experiment, you would not get this p hat. Getting this p hat is very similar to what we discussed before about the coin, that it takes 6 flips of a coin to get 6 times in a row tails. When you flip a coin, it's only like a 1% chance. Same thing here. This is only like a 1% chance. So let's just do the calculations to concrete this in. So there's our z-score, p minus mu p hat divided by sigma p hat. Calculate that. So plugging in this value minus this value, so the distance, divided by 0.049. Basically the same thing as we did in our mind. It's just 3.06, a bit higher than 3. And so now if we calculate the p-score, so let's, well, we don't calculate it, we just look at the table. Let me find that table over here. So if we now calculate 3.06, and it's important to remember, it's always the whole area on the left. So from here to the left. So you'll have to subtract something from that. Well, 1, we need the area on the right, so we just subtract 1 minus whatever we get. So 3.06 is 3.006. There it is. So 9989. So let's have a look. P minus 1 minus 0.9989, 0.11%. So this is not 11%. This is 0.11%. So the result is 0.0011. And then if you turn the percentage to 0.11%, so it's less than 1%. Sometimes this can be a bit confusing when you go from here to percentages, and then you might think it's 11%. It's actually 0.11%. And so as we discussed, remember that example of the coin toss, there's only a 1% chance to get 6 tails in a row. Well, this is even less than that. This is like getting like 9 tails. 9 times you flip a coin and you get tails every single time. So that is even less than what we had before. And, you know, like in your experience, how often would you get 9 tails in a row? Very low, very unlikely. So that's why this is a very unlikely hypothesis, a very unlikely universe that we live in, that we know that these things are distributed like that from the central limit theorem. And we still managed to pick out 73 households with, or 100 households, out of which 73 of them had tablets. So therefore, this is just like in our universe, it's very unlikely, close to impossible. It's a 0.11% chance of that happening. And it's definitely less than 3% chance, because we were asked to test a hypothesis of a 97% significance level. So it's definitely less than 3%. So therefore, with a 97% degree confidence, we can reject the null hypothesis and accept the alternative hypothesis. In fact, as you can see from here, we can even reject the null hypothesis with a 99% confidence, with a 99.89% confidence, so a very high degree of confidence. But since we are asked to do the 97%, we're doing 97%. And by the way, since you have this alpha, you can take that approach with the rejection region if you'd like to. That might be some good practice to look up 97% in the p-value table and then calculate the Z critical and do the same problem, but through the approach of rejection regions. So there we go. I hope that was useful, and I'm glad we had a chance to go through the intuition behind things so that you kind of can see how to think about these things intuitively. And as you can see, even just by selecting only 100 random households, not thousands, not tens of thousands, but just 100, we can get such strong results, like a 97% significance level. Well, partially it is attributed to the fact that it's changed so much, so from 58% to 73%. If it was like, if you select 100 random households and you only got 61%, then this would be different, because this would be the same, this would be the same, this would be different. So this would be less, 0.61, and this would be less. So, and this would be much smaller. So it wouldn't be 3.06, it would be much smaller, and therefore you wouldn't get that. So another good exercise for you, if you like, is to just kind of experiment or do like reverse engineer this problem and find out at which level, what number you would have to have here for this to be exactly 3%. So at what level, if you found how many households to have tablets out of 100, would you not be able to reject the null hypothesis? That's a good exercise as well it'll help you understand when you reverse engineer a mathematical problem like this. So you're kind of like creating it yourself, you better understand what's going on in the background. So it's a great opportunity for you to practice if you like. So what number has to be here instead of 73 for this percentage to be exactly 3%? Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.